Okay, so today I'm going to be talking about trigonometry. Now, trigonometry at first glance might seem like a dry subject, and oftentimes perhaps it is presented in that way when we're studying strictly the sort of mathematical properties of right triangles. However, we're going to expand our discussion a little bit to include circles, and then we'll see immediately once we get into that the language of trigonometry and the mathematical tools of trigonometry could be immediately applied to other cyclic phenomenon like sound or light or any other wave phenomenon, which then broadens the discussion quite a bit, because now we can discuss things like pleasing sounds or music or much more aesthetic topics, which at first glance might seem like it's beyond the realm of mathematics to discuss. All right, so we start the discussion by talking about right triangles. Now, a right triangle is simply a triangle where one of the angles is at 90 degrees. Now we label the side lengths, the lengths of the side A, B, and C. And then we label one of the remaining angles with the Greek letter theta. Okay, and the units of the angle are degrees. Now, there are alternate names for these, the sides A, B, and C. The longest side is also known as the hypotenuse. Now, if the side shares, or if a side A in this case makes up one of the legs of the angle theta that we're concerned about, it'll be labeled as the adjacent side. So it's adjacent to the angle in question. And in our case, as shown here, the side length B will be the side that's opposite of the angle in question. Okay, and a property of triangles in the plane is that their angles sum to 180 degrees. So if I have one of the angles, because this is a right triangle, one of the angles is necessarily 90 degrees, and then I set the value of the angle theta, then the third angle is necessarily going to be 90 degrees minus the angle theta. Okay, and then sort of one of the underlying theorems that governs trigonometry is the Pythagorean theorem, which simply states that if I have a right triangle, then if I square the lengths of the two shorter sides and sum them together, I will get the square of the longest side. Okay, now we're going to discuss the applications of the Pythagorean theorem, but we won't derive it. Okay, along with defining some of the terms there, we're going to also define some of the two functions, and these are going to basically be some of the main focus of what we're going to be talking about. And those functions are the sine and cosine functions. And they take as their argument the angle theta, and they're defined as the ratios of the side lengths. So the sine function takes the ratio of the adjacent side, or I'm sorry, the opposite side divided by the hypotenuse, or in our case, B over C, and that's simply its definition. Then also we'll define the cosine of the angle theta as the adjacent side length divided by the hypotenuse. Okay, so these are definitions. And a third function we can talk about, although its importance, it's essentially a combination of the other two. So, in my opinion, isn't as important as the other two. The other two are more fundamental. As the tangent function. Now that takes as its argument theta, and then spits out its value is the ratio of the opposite side divided by the adjacent side. And you can see that this is really, if you divide the other two definitions, you'll see that you arrive at the same thing. So the tangent function is a little redundant. Now there's this mnemonic to help you remember these relationship, and it goes SOHCAHTOA, right? So where the s is related to the sine function, and that's going to be the opposite divided by the hypotenuse, which is in our case the opposite is given by the side length b, and the hypotenuse is given by the side length c. Then you have the cosine is the adjacent side divided by the hypotenuse. So the cosine of theta is going to be the adjacent a divided by the hypotenuse c. And then the tangent function is the opposite side, which is b, divided by the adjacent side, which is a in this case. And so what we're going to be studying, a lot of what we're going to be talking about in the upcoming couple minutes here is the applications or the relationships between these sines and the angle theta, the sine, cosine, and these functions anyway, as they relate to the angle theta. Okay, so now we'll discuss a concept of which allows us to simplify our discussion, but we're going to discuss the concept of similar triangles. Okay, now similar triangles are ones where we simply scale the lengths of the sides. We hold the angles constant and we just scale the lengths of the sides. Okay, so if we hold the angles constant, then if I double the side length a to arrive at a prime, so a prime is twice the value of a, then I would have necessarily doubled the length of b to arrive at b prime, and double the length of c to arrive at c prime. Which means if I hold the angles constant, so if I hold theta constant, then the ratios of the sides will also remain constant, and therefore the sine and cosine functions will remain constant. So they, in other words, the sine and cosine functions are independent of the scaling of the triangle. So if I double all the side lengths, sine and cosine don't change. Okay, this allows us to restrict the discussion to one particular triangle, and customarily and most sort of conveniently, we set the value of the hypotenuse, the length of the hypotenuse, to one unit. Okay, then we can simplify the discussion that the sine of the angle theta is simply the length of the opposite side, and then the cosine of theta is going to be the length of the adjacent side. So this simplifies our discussion, and then we know that we can just scale it back up to arrive at whatever application that you're currently dealing with. All right, to be useful, I'm going to need numerical values for the sine and cosine functions. What I mean is, if I give those functions an angle theta, I need to get a number back so that I can apply it in my real world situation. Okay? And this is possible in a couple, well, it's we can derive these values exactly in a couple of situations. One of them is when the value of the angle is equal to 60 degrees. And I'm going to go briefly through the derivation for how one would do this. Okay, we would start with an equilateral triangle. And an equilateral triangle is one where the side lengths are all equal to one another. Okay, and as a consequence, the angles are all equal to one another. And if they're equal to one another and they have to add to 180 degrees, then they're necessarily 60 degrees. So all equilateral triangles have three angles of 60 degrees. Okay, and in this particular situation, it's convenient for me to set the length of the sides to 1. I start by dropping a perpendicular line from this point C down to the midpoint of the line between A and B. So therefore, we know a couple things happened when we did that. We formed a right triangle, by dropping that down to the midpoint. And we now know the value of the side length A. It's going to be half of the length of the line from A to B. So therefore, we know that that side length is 0.5. Then we apply the Pythagorean theorem. So we have, here's A squared plus B squared, the unknown value, is going to be equal to 1 squared. And then with a little bit of algebra, we arrive at the value for B. Now, it's going to be important later that we had to compute the square root of 3 in this calculation. Okay? Now, I want you to hold on to that. Hold on to that fact. Okay? So once I know the lengths of the sides, I can basically, just off of the definition of what the sine is, I know the sine is the opposite over the hypotenuse, which just comes to the 0.866 value, and then the cosine is just going to be the adjacent over the hypotenuse. Okay? And I also want you to recognize that if I know that this angle is 60 and this angle is 90, then this angle is also known. And in this case, it's going to be 30 degrees. So we just calculated the sine and cosine of 60 degrees, but we got the sine and cosine of 30 degrees for free. If I know the sine and cosine of 60 degrees, then I necessarily know the sine and cosine of 30 degrees by swapping the opposite and adjacent terms for A and B, side lengths A and B. In other words, the cosine of 60 degrees is necessarily equal to the sine of 30 degrees because the values of the opposite side and the adjacent side have just swapped. Okay, and likewise for 60 degrees, the sine of 60 degrees is equal to the cosine of 30 degrees. Now, in practice, the way this is actually done is you simply plug it into a calculator. Okay, if you want to know the sine of 60 degrees, you plug it into a calculator. And this may seem like a cop-out. However, remember that in that calculation a second ago, we had to calculate the square root of 3, which, if you're satisfied with writing the square root of 3, is fine. But in practice, if you want a numerical value, the only way to arrive at that is to plug it into a calculator. Now, when you do this, you got to be careful of things like make sure that you're using the right units for your angles. This brings us to our first use case for trigonometry, namely describing points in a plane. Now, typically when we try to describe points in planes, we first set up a set of coordinates, axes, x and y typically. which are, they're perpendicular axes typically. And now we can describe any point, in this case, the point P, as a set of coordinates. We require two coordinates, and we label them also X and Y. And the coordinates describe the distance that would be required to travel in the X direction, and then followed by the Y direction, to arrive at the point P. So I traveled a distance X in the X direction, and then I traveled a distance Y in the Y direction to arrive at the point, and then I can label the point with those distances, X and Y. Okay, now this implies a right triangle. We have a right angle here because of the fact that X and Y, the X and Y axes are perpendicular to one another. And so every point on the plane implies a right triangle. And then we label the hypotenuse R for reasons that'll be clear here in a second. However, I want to address a certain thing that is common in all of mathematics, is that once we start changing context, the notation changes. So we went from A, B, and C to X, Y, and R, but I'm leaving that in here, and I'm intentionally switching so that you can see the relationships between them, and then understand that this is ubiquitous throughout mathematics. The notation changes routinely. So what's more important is to understand concepts that underlie that stuff, and try not to memorize formulas and stuff. That you're going to find that if you try to learn mathematics, it's just a necessary thing you're going to have to contend with. Now, just like before, we discussed how scaling of the triangles had no effect on the functions of sine and cosine. Same is true here. So we can limit our discussion to the points which lie a distance 1 from the origin, typically. And those points describe something known as the unit circle. So every point on this circle lie a distance of 1 from the origin. Okay, so and I can arrive at any other point, say say a point here or a point here, simply by scaling this triangle. So once I have, I guess it's sufficient for us to discuss the points that lie on the unit circle, because we can expand that just through scaling of our discussion, or scaling of the relevant coordinates to arrive at any other point. Okay, and because we're interested in the angles only, this simplifies our relationship, so that like now we can take the cosine of this angle theta and arrive at the x coordinate, and likewise for sine, we can take the sine of the angle theta and arrive at the y coordinate. Okay, now when we shifted to circles, we allow for a broader definition of what this angle theta was or is. Like if in the context of a triangle, the angle theta having a value of 90 degrees is not possible. You no longer have a triangle. Or what if the angle is greater than 90 degrees? So this allows us to expand our definition of the angle theta. And so this is usually done in the context of a particular convention. And the convention is that if measured counterclockwise, the angle theta has a positive value. Okay, and it can also wrap all the way back around. So like we can have angles that go all the way back up to 360 degrees or even beyond. 720 would just be two times around the circle. And then again, we have the concept of a negative angle. Like if you're going clockwise, if you're going clockwise, then the value is negative. Okay? And you can arrive at the same point so the same point, xy, can be described with, say, in this case, an angle of negative 45 degrees or so. Or it could also be described as positive, let's see, like, I don't remember. Let's see, 315 or so. Okay, so they describe the same point. Now the angle theta can vary, although my little slider here only goes from negative 180 to 360. In theory, that angle can go from negative infinity all the way to positive infinity. Now, when you start studying trigonometry, if you did it in a classroom setting, you would spend most of your time studying the consequences or deriving directly these identities. There's a whole series of trigonometric identities, and I've pulled out a couple that I find to be the most useful. And in my practice as an engineer, or as a just someone who's interested in science, these are the ones that I've found to be the most useful. The rest of them come into play, like if you're trying to simplify expressions and stuff like that. But I don't even know if that's all that important anymore nowadays. However, these are the ones that are most useful to me. One is simply a restatement of the Pythagorean theorem in terms of the functions sine and cosine, which, if you go back and remember, the Pythagorean theorem is just, using this notation, would just be x squared plus y squared is equal to 1 squared, right? Y squared is equal to the sine of theta squared. X squared is equal to the cosine of theta squared. So a restatement of the Pythagorean theorem is just that the sine of cosine, or the sine of sine and sine of, the square of sine plus the square of cosine is equal to 1. Okay? And then alternatively, this gets into a little bit of, I'm not going to go into where these come from. This would be a little bit beyond the scope of what we're dealing with here. But there are methods by which you can you can sum angles and arrive at their cosine and sine functions based on the sines and cosines of the individual angles. And so I find these two sets of identities, the Pythagorean identities as well as the angle sums and differences, identities, to be the most useful. What I find to be a very useful resource is the Wikipedia page on the topic. And whenever I'm having to deal with trigonometric relationships in my daily work, I frequent this page, and it's excellent source of information if you're interested and you want to read more on it. Okay, and then finally, just to touch briefly, what we've discussed so far, especially in the context of circles, you can kind of see right away that we can immediately see that in the context of a circle, we have a method for discussing things that are cyclic in nature. You know what I mean? So as like one revolution through the circle is one cycle. And so that you can see, at least partially, how we can start to expand our discussion into things that aren't necessarily geometric in nature. We can start talking about things like waves, where if we just take the y coordinate all by itself, in this case, y is equal to sine of theta, right? If we use theta as like an independent variable here, now we have something that can vary with time, or I'm sorry, vary with anything. We have these cyclic phenomenon, and this gives us a whole new language with which to discuss things like sound or light, everything that would require a language focused on the discussion of waves and things like that. And, this allows us to broaden our understanding quite a bit to include things like what makes a sound pleasing, or some combination of sounds, or how do sounds combine. And that leads to a whole theory regarding, say, interesting topics like music, or things like that, or so I guess my point is that if we see how these concepts, and in this case trigonometry, these underlying concepts can be built upon to arrive at things kind of unexpected. So we started talking about right triangles, and now we're talking about a language with which we can describe, the harmonics of a particular instrument, say, or entire music theories based on mathematics. So I think these sorts of connections are what I find very fascinating, and I think would actually allow for a much broader appreciation of these underlying topics if they were included in the discussions when these things were being originally conveyed to students. And so I just hope to leave some people with a little bit of an appreciation for the beauty that can come from mathematics, and that it's not as dry of a subject as you may have understood it to be. So thanks a bunch. If you have any questions, you maybe drop a comment or something. Maybe I'll do this again. It was pretty difficult, so maybe not.